In fact, we collaborate together with FAO, and we are often visitors to Latvian Laser Center as well. So I will so we already heard history, we already heard about the applications, so I will touch upon the engineering side more or less. And sometimes, indeed, these NV Diamond sensors can be easy, but sometimes it's really, really challenging. So first of all, I represent Institute of Electronics and Computer Science. It's quite near here. And if you really want to summarize everything that we do in a single sentence, you could say that we specialize in the development of smart embedded cooperative systems. Of course, it's lots of applications, broad applications, etc. So we are very fortunate. We have many, many international collaborations, and we are really active in European scene, especially CHIPS-JU and Horizon Europe frameworks. I myself, I'm the lead of the Laboratory of Integrated Circuits and Systems. I'm really proud of that, and I'm proud of our group. And here on the right side, you see one of my favorite, if not the most favorite picture that basically exists anywhere. So it actually comes from the computer architecture, and the baseline idea is very simple. All the technology around us, we can split it in multiple abstraction levels. And so let's say physics is, of course, underlying foundation for everything, but if you want to build transistors, you use physics, yes? You combine transistors to build digital electronics, and so on, up to an algorithm and use case. And in computer architecture, there's this idea, if you really want to make something new, you have to be an expert in multiple layers, yes? Probably many of you have programmed in Python or something like that, so you know, actually, if you know how the processor is built, you're a much better software developer. Yeah, so this is this kind of idea. There's another way how to view this relationship. It's about universality and performance. So the most universal computing technology that we have at the moment is a processor, yes? Processor runs your operating system. It can do calculations ranging from chemistry to astronomy. So it's a great tool. But in fact, because it's so universal, it's not very efficient. So processors are actually very, very inefficient if you check, for example, power performance. That's why you have GPUs for video processing, right? If you go to the other side of the spectrum, the most efficient thing that we can have for any computation is application-specific integrated circuit. It basically means you create a chip for this particular specific application. So again, in my lab, what we do, we actually specialize in these multiple technologies. So if you combine them, you can say this is, it's a heterogeneous approach, yes? So it's really kind of, I must say it's really interesting to work with these different kinds and variety of technologies, but it's also really demanding. So even if, let's say, a new person joins our team, just 2 or 3 months, we have to train them, even if it's a master student. And one of our main kind of research development areas is, in fact, development of new sensors. Because of our knowledge, we are actually well situated for this. We can interface with the physical phenomena at really low level and then actually bring it to the actual use case and applications. So we have built stereo cameras, we have built infrared cameras, perception systems for automotive, and at the moment, also, we are working on quantum sensors. This is our research timeline. So again, we are really fortunate to, basically all of these are international research projects with different topics, but basically the main overarching idea is to actually develop this NV diamond-based quantum sensor that's actually applicable, that we can use, that we can basically sell, that's kind of product-oriented. So yeah, again, there's lots of partners that we also collaborate with, including like Mercedes-Benz, AVL, and in fact also FAO, yes, this Institute of Applied Quantum Technologies. I will not go into details again how quantum sensing works, but this picture, although it seems simple, for an engineer, there's lots and lots of challenges. So the actual measurement indeed looks like the picture on the right side. Yes, so there are 2 peaks, and all we have to do is just measure these frequencies of these peaks, and then we can infer magnetic field. Reality is much more difficult than that. So first of all, there are not 2 peaks, but there are 8 peaks. because of the diamond structure, yes. So actually, it's a mess already. Then you also need this bias magnetic field if you use in this configuration the sensor. So it means you already have some extra design here. Further, you have optics, so that you have to supply green light to the diamond itself and collect and read out the red light. And the favorite part of all, simultaneously you need microelectronics. So in the previous slides we saw like a small loop antenna for magnetic field, but this is the thing, the difference between like a physicist approach and engineering approach. If you actually use like a single wire for microwaves, it kind of reflects 99% of all the power. And suddenly you need an amplifier which is this big and costs like 2,000 or 3,000 euros. So basically, our goal here at EDI is to reduce these costs, to see how low we can go. This is one of the examples that we actually developed together with FAO. This will show the European event at FX. Here you can see one of the configurations, one of the possibilities how this quantum sensor can look like. So here, in fact, what you see, it's just a fiber, and the diamond is actually glued onto the fiber, optics fiber. And these big boxes that you see around it, those are in fact magnets, just to create this biased magnetic field. And in this case, you even don't see the whole electronics yet. So this is one of the earlier earlier setups, yes. So our role is actually to create this kind of subsystem, yes, so of this quantum sensor, so that it's efficient, integrated, etc. So as I told you previously, there are optics, there are analog electronics that are quite demanding, and further, we leverage our know-how with digital electronics so that we can perform measurements at the lowest possible level, so that we can reduce any latency. And of course, on top of that, we have to provide software and interfacing to actually work with these sensors. It's quite a complex challenge, but it's very fun. So that's already good. Next, just a couple of ideas, a couple of things from day-to-day engineering and research. The development is very messy. So this is how our setup looks like. Actually looked like a couple of months ago. So you can see lots of modules, lots of wires, lots of opportunities for mistake. And in one of the review meetings, I was even called European MacGyver. Yeah, because I set up the sensor for like 2 hours, and I missed one of the optic connections, and I had to fix it. Yes. Or there are procurement issues, yes, in all the public institutions. For example, we didn't have a holder for a filter, so we had to make one on our own. Yeah, so further, again, I'll just stress this out. Development is very complex. In fact, you can also see, for example, these sensor heads, the laser, if you can see it here. This is, in fact, produced at FAO. So my colleagues went to FAO to actually make a copy for us here as well. Here on the right side, for example, this is the diamond itself, and it's actually glued into this hole into the PCB. So there's lots of these layers of complexity, right? So you need simultaneously the light and everything. So that's quite a lot of stuff. And here's, for example, the example, like this is also iteration of a sensor head, where it's just a fiber and the diamond is literally glued onto it. So depending on the use case, you have a variety of these configurations that you might use. Now I'll share one of my probably favorite difficulties or challenges or funny parts. I hope that the project writing team never sees this slide. So I have a sentence here that's actually from the grant agreement, yes? And it says that basically the diamond, this quantum sensor, will be used for motor control. Probably, and this is a mistake. It shouldn't be used for motor control, and I'll explain why, and probably what happened. So probably a physicist had a discussion with a motor control engineer, and the motor control engineer just asked, like, hey, can we measure AC magnetic field? And the physicist said, yes, of course, it's easy. So basically, you can configure diamond in a specific way to measure, indeed, time-varying magnetic field. The motor control engineer actually thought by this that you have a time-varying magnetic field that you need for motor control. This is the actual measurement that you do. But in case of physicists, it's more like a configuration with pulses, where you set the diamond in such a way that you bombard it with light and microwaves, and you basically detect just a single component in the Fourier spectrum of the AC field, which is not usable for motor control at all. So I love this example because this kind of illustrates this gap, even in vocabulary. We kind of use the same words, but it means different things. And from one side, yes, we could say this is a mistake. But on the other side, it just makes our life much more fun. And we have cool requirements, like achieving a sample rate of 5,000 kilosamples per second. So if you go to like physicists, like maybe setups, often enough you'll see like sample rate of 1 measurement per second. Maybe a bit more. So here, this is one of the later demonstrators. So you can see that spectrum itself is actually not changing at all. It's because we are not measuring it. So we're measuring just specific points. And this is digitally enabled. And here we now achieved like 45 samples per second with redundancy. And now, although initially what seemed a mistake, now we see that, yeah, in the future, until the end of this year, we must and we can achieve 5,000 samples per second. Yes. In our cases, there's lots of requirements. There's compactness. This is something that we work together with our partners. There's latency. That's why we leverage these digital control ideas. Because, for example, if we use quantum sensor for localization, it doesn't matter. We can wait actually for a longer time, especially if it's some use case with the robots or search and rescue, for example. But if you want to use it for real-time control, it's totally different story. And this is what we optimize for. And finally, I think one of the biggest challenges is, in fact, integration. So if you want these quantum sensors to actually be like a viable product, it must be easy to use them. Because there's even in our case, we have been approached by universities just asking, could we buy the setup itself? Because they would actually want just to explore applications, how you can use the sensor. So I think this is something that will change in the future. There will be this new kind of research field of, just trying to find new and new use cases. So there's opportunity here as well. So I was brief. Thank you very much.